The Chinese remainder theorem finds its application in a variety of domains, including cryptography. In this lesson, we'll first understand the Chinese remainder theorem itself, and then we'll reconstruct a key expression used in low exponent attacks. That will be helpful for our discussion up ahead. Then we'll take a look at Håstad's broadcast attack, which is a type of low exponent attack, and then we'll wrap up with a sample. The Chinese remainder theorem is a mathematical tool that helps us solve problems like find a number that leaves specific remainders when divided by different numbers. Imagine you have a mystery number, and you know that the remainder it leaves when dividing by several numbers have no common factor. All of this mystery number is divided by several numbers that have no common factors between them. CRT, or the Chinese remainder theorem, tells us that there is one unique solution that fits all those criteria conditions. Formally, we can say that given n congruencies, we can uniquely solve every pair of congruencies having relatively prime moduli. What this means is these numbers 7, 3, and 5 have the greatest common divisor of 1 when taken pairwise. The GCD of 7 and 3 is 1. Likewise, the GCD of 5 and 3 is 1, and so on. Before we dive any further, let me explain what you can expect out of this lesson. All the lessons in the next few sections are a build-up for the Hostad's broadcast attack. Our goal here is to find a unique solution of a system of three congruencies, and in lieu of which we will remodel the CRT theorem into the expression as you see right here. This will help us demonstrate the attack. The goal of the lesson is not to prove the uniqueness of the solution. And if you are looking for a formal proof, you may check out the content by Keith Conrad at UConn, University of Connecticut. He has documented a formal proof by induction. You may find the link to that document in the description section. We are given a set of three congruent equations. The modulo n1, n2, and n3 are pairwise coprime. What this means is each pair has no common factor other than 1. What that also means is the GCD, or the greatest common divisor between n1 and n2, is 1. Likewise, the GCD between n2 and n3 is 1. And similarly, the greatest common divisor between of n3 and n1 is also 1. Now, CRT, or the Chinese remainder theorem, states that there is one unique solution for the system of equations, which is x modulo n, where this n is the product of all moduli n1, n2, and n3. In general, if you have k congruencies, k different congruencies, like these, then the CRT tells us that a unique solution can be found guided by this formula. In this formula, AIs are the remainders from each congruencies, which is A1, A2, and A3 that you see here. YIs are N, which was the product of all moduli, over Ni for each expression. For the first expression, Ni is N1, for the second, it's N2, and for the third, it's N3, respectively. Now, Zi is the modular multiplicative inverse of yi's that we have just calculated. With respect to ni's, which is modular multiplicative inverse of yi's modulo ni. Here again, the ni's are n1, n2, and n3 respectively. What this also means is the product of yi and zi must be congruent to 1 mod ni. When we plug these parts into the formula, here you get the unique number x that satisfies all given congruencies simultaneously. Now let's go step by step for a system of three congruencies. Suppose we have x congruent to c sub b mod n sub b. Another equation which is x is congruent to c sub c mod of n sub c, and another which is congruent to c sub d mod of n sub d. Now, our first step over here would be to calculate capital N, which is nothing but the product of all moduli NB, NC, and ND. Now, our next step would be to calculate yi's, which is y1, y2, and y3 corresponding to each of these equations. Now, a variety of textbooks use different notations for the same expression. Yi's are also represented as ni's, and here ni's take the form of expression in the form of nb's, which is equal to yi, nc, which is equivalent to y2, and nd. So yi can also be expressed as ni, y1 can also be expressed as nb, y2 can also be expressed as nc, and y3 can also be expressed as nd. At this point, it's important for us to recap how these values are computed. So yi's are computed as n sub ni's, n over ni's, and this can also be written as ni's. Let's do that for each equation. So nb, which in our expression would be y1, is computed as nb times nc times nd over nb. So we are left with nc times nd, and that's our y1. That's our nb. For y2 is also nc. We have nb times nc times nd over nc, and we are left with nb times nd. Similarly, for our last equation, which is y3, also we can also represent this as nd. We have n sub b times n sub d times n sub c over n sub d, and we are left with n sub b times n sub c. At this point, we have computed all of our yi's. For each congruence, again, y1 was n c sub n sub c and times n sub d, y2 was n sub b times n sub d, and y3 was n sub b times n sub c. Alright, now we need to calculate zi's. And if you remember this right, zi's are the modular inverse of yi's corresponding to ni's. So yi corresponding to Zi is yi inverse modulo corresponding to its ni. So mod ni. And that's what's written over here. Y1 times Z1 is congruent to 1 mod NB. Y2 times Z2 is congruent to 1 mod sub n sub C. And Y3 times Z3 is congruent to 1 modulo n sub D. Now, we already have the values for Y1, Y2, and Y3. Let's plug it in and calculate the Z's. For our equation, Z1 would be Y1 inverse of that, modulo NB. And that would be NC times ND modulo NB. Similarly, for Z2, we have Y2, again, inverse of that. In the previous equation, we missed the inverse of the whole thing. So Y2 would also be inverse and mod n sub C, which is, we already know the value of Y2, let's just plug it in. NB times n sub D inverse of that, mod NC. Now for the last Z3, we have Y3 inverse mod ND. What that would mean is we already got those values over here. Just plug it in. It's NB times N sub C inverse of that mod NC. Now we have our yi's, zi's, and ci's or ai's. It's time we compute everything. Our final substitution. So we have a final substitution with us. We know the value of CBs. CBs are also a way to represent ABs, which were nothing but the remainders. The remainder from each equation. All right. So we have with us CB. We already know the value of Y1, which is N sub C times N sub D. We already know the value of Z1 at this point, which is N sub C times N sub D inverse of that modulo NB. That is the expression that we need to calculate for the first one. We've simplified it. We've simply substituted the values that we've calculated. That's the first expression. Similarly, the second expression would be N sub C. We already know the value of y2s at this point, which is N sub B times N sub D. We already know the values of Z2 at this point, which is N sub B, N sub D, inverse mod N sub C. And while we are at it, let's also do Z3, the third component that is. The third component is CD times, we already know the value of y3. Yes, that's NB times NC. Then we know the value of Z3, which is NB times NC, inverse of that mod ND. There we have the complete tree substitution. Now that we've computed each of these expressions, we have reconstructed the special formula that we wanted to from slide 1. This is the same thing as what we did in the previous slide. Note that the shorthand notations for NB, NC, and ND are just constructed over here. We are using the shorthand notations for these things. NB was nothing but NC times ND. And NB inverse is nothing but the inverse of this thing. So over here, we are only using the shorthand notations of the things that we've already discussed. And now we have reconstructed our special equation that will help us demonstrate the Håstad's broadcast attack. Next up, let's see what Håstad's broadcast attack actually is, and then we'll dive into the mathematics of it. Håstad's broadcast attack is a type of low exponent attack, where the exponent e, the public exponent, is usually chosen as 3 or some other low value. For a quick recap, in the RSA crypto system, if we want to encrypt a message, we compute C, which is the ciphertext, is m raised to e mod n. Here, e is the public exponent, and e and n is the private public key. Now, historically, this value of public exponent was chosen as 3 or any other low value because that helped increase the performance. In the year 1985, John Håstad highlighted the broadcast attack, which illustrates the dangers of using a low exponent, it's just 3. Let us understand the setup of this attack. We have Alice over here, the sender of a message. She wants to send a message M to 3 different recipients: Bob, Carol, and Dave. It's basically a broadcast to 3 different recipients. Now, Alice chooses the modulus N1 for Bob, N2 for Carol, and N3 for Dave. And all of these are relatively coprime. Now, the ciphertext C1 is computed as M3, M raised to 3, because Alice chose the public exponent to be 3, mod N sub 1. For Carol, the ciphertext is M raised to 3, mod N2. And for Dave, the ciphertext is M raised to 3, mod N sub 3. Now at this point, the channel is insecure, and E was able to intercept all of these ciphertexts through one of the other mechanisms, such as man-in-the-middle attack. The channel itself is insecure, and the ciphertext can be intercepted by Eve. So Eve intercepts all these 3 ciphertexts. At this point, Eve has C1, C2, C3. Let us also recollect that the public exponent and the moduli itself are also public knowledge. What's not a public knowledge is M3, M raised 3 rather, because E was 3 and the chosen message was N. Håstad proved that Eve, or the adversary, can reconstruct M raised to 3, and then to get the ciphertext or the plain text itself, they compute the cube root of this computed X. Even the adversary can reconstruct this plain text even though they do not have access to M, or they don't know M3 as a matter of fact, M raised to 3, but they can recompute M raised to 3 and thus take the cube root and get the original message M back. This was the threat of using a low exponent in RSA encryption. Let's dive into the mathematics of it up next. To begin with, we are given 3 ciphertexts, or rather, Alice computes 3 different ciphertexts. CB, which is sent to Bob, CC, which is sent to Carol, and C sub D, which is sent to Dave. In all of these, Alice decides to choose the public exponent as 3. The moduli that Alice uses for each of this computation are NB, NC, and ND respectively, which is relatively coprime, or the GCD of NB and NC is 1. Similarly for the other two pairs. Now, we'll take a sample numbers for our example. We'll say the public moduli that was used for the computation of ciphertext sent to Bob was 187. The one used for Carol was 115, and the one used for Dave was 87. At this point, let's compute the ciphertext that Alice calculates for each of these recipients. Alice chooses M to be 42, and the public exponent is 3. This is in Alice's part. Again, in RSA, we compute the ciphertext as M raised to E mod N, in this case Ni, and this is what we are doing. So for Bob, it's 42 raised to 3 mod 187 because we chose the modulus to be 187, and it gave us the result 36. For C sub C, it's the ciphertext is 28, and for C sub D, the ciphertext is 51. These are the ones sent to Bob, Carol, and Dave, respectively. Now, on Eve's part, Eve now has access to E, NIs, and C1, C2, C3 because they have intercepted these ciphertexts. Now, they can construct N, which is the product of all these moduli, and it comes to this large number. Then Eve will calculate the yi's, or in this notation, we'll call it the ni's. For NB, it is n over n sub b, which was this large number that we just calculated over NB. And we get a number 10,005. Similarly, we calculate this for NC, this number over NC itself, and we get a number, the NC component of our equation. Similarly, for ND, we get a different number. Now, Eve has to construct ZBs, which was the modular inverse of NBs, or the NIs that we just calculated. Again, in certain textbooks, we have different representations, and we want to know all of these. So ZBs could also be represented as MB, NC, and MD, respectively. Again, they were modular inverses of the things that we calculated right before. So ZB is the modular inverse of NB modulo NB. ZC is the modular inverse of NC mod NC. And ZD is the modular inverse of capital ND mod ND. Now, we can calculate these inverses using the extended Euclidean algorithm. And once we have it, we have those values as 2, 49, and 49 by coincidence. MBs and MC are MD and NC are 49 by coincidence. The same values. At this point, Alice, Eve has everything they need to plug in the formula AI, YI, ZI, or to reconstruct or to know the other expression, we say CI, NI, and MI. These are just different notations for the same things. Now, at this point, Eve is ready to plug this in. They know the value of CVs, NBs, and MBs, CIs, NIs, and MIs rather. Now, Eve can simply plug those values in, as we have calculated this right now, and get this huge number. They have to calculate the modulus of this number, so it's within the range of this. And after doing a mod operation, the final ciphertext or the clubbed message is this. This is M cube itself. If we calculate the cube root of this number, we get 42, which was what Alice sent out with. This is what Alice started with. Alice encrypted 42 itself. And Eve is able to reconstruct this, even without knowing any of the major data such as M, Q, or M. The only thing in possession of Eve were N, E, which was public information by that time, and the intercepted ciphertexts. And they can compute this. This is only possible for a low exponent, and that was the threat of a low exponent attack. And that is how the Chinese remainder theorem plays in the Håstad broadcast attack. This video takes inspiration from a variety of sources, including the Wikipedia page of the Chinese remainder theorem itself, and a special document by Keith Conrad, who's a professor at University of Connecticut. In this document, Keith has shown the formal proofs for the uniqueness of the equation that the Chinese remainder theorem provides. You may want to go through them, and the link to these references is in the description below.